Hello everyone, greetings from Chemnitz University of Technology in Germany. I'm Michael Ding.
And I am Hannes Kissner.
In this video we will talk about how we apply different machine learning algorithms to impedance spectra measured by capacitive proximity sensors for material detection. Let's start with a short introduction to capacitive material detection. Objects influence the electric fields between two capacitive plates differently, depending on their materials and their permittivity. We can take advantage of this effect and provide a new sense of perception for robots. For example, when capacitive sensors are placed within robotic grippers, the robot can detect what material the object is made of, even though several different objects may be identical in texture and shape. We could also detect whether a glass cup is empty or filled. Based on this knowledge, the gastric force can be adjusted, for example. Now attached to robotic feet, the walking pattern can be adapted according to the material on the ground. For household robots, such as vacuum cleaners, different suction modes can be activated depending on the ground. Material detection is therefore an important perception for robots, which enables the robot to better understand its own environment. Compared to tactile, visual, or electrical sensing methods, capacitive sensing has several advantages. First of all, it is contactless and non-destructive, which means probes for direct electrical contacts are not required. This also means the sensing method can penetrate surface layers such as paint or oxide layers, which may affect tactile, visual, or direct electrical measurement methods. In our work, we measure the capacitance at different frequencies, which is nothing else than electrical impedance spectroscopy, performed capacitively. The permittivity of individual materials differs slightly at different frequencies. However, the question is how we can infer the material from the impedance spectra. In our work, we have two main objectives and contributions. First, we want to evaluate the performance of different machine learning algorithms for the material detection task. And second, we also propose a new method for converting impedance graphs to images, and then using neural networks for image recognition for classification. The idea behind this is that we found out that as humans we could differentiate some of the images by looking at the graphs. In the tactile domain, several approaches have been shown using machine learning to classify materials from tactile information. In capacitive measurements, material detection is not a new task, since it is required to achieve accurate proximity measurements. This is usually achieved by analyzing permittivity. In our previous work, we started analyzing capacitance or permittivity at different frequencies with impedance spectroscopy, but with the main focus on the spectroscopy part itself. Now we want to investigate how machine learning can improve classification tasks. Alaki et al. Demonstrated the first application of machine learning for material classification with capacitive data and measurements from different directions, similar to triangulation. Jean et al. Showed promising results of material classification with neural networks and tactile capacitive measurements for object sorting. Also not directly related to robotics, but supporting works were carried out in the field of meat quality detection with impedance spectroscopy and breast cancer detection with impedance spectroscopy combined with neural networks, which showed promising results with the use of impedance spectroscopy and machine learning. Next, we will discuss the measurement hardware. The sensors are originally used for proximity detection and proximity zeroing tasks, where the sensors are mounted on the outer shell of the robot to detect obstacles. We use a single sensing element from the system, which uses time of flight to detect obstacles for far range, but with narrow field of view. In case obstacles are undetected by time of flight measurements, capacitive sensing is used as an additional safety layer with this wide but close range coverage. The capacitive sensor has two electrodes where differential signals are applied to detect changes in the electric field caused by obstacles. For the material detection, our dataset consists of 200 measured spectra for each of the 9 different materials. A single spectrum looks as follows. It has a frequency range of 20 kHz until 1 MHz. It is split to real and imaginary parts, which results in 2 by 980 data points for each spectrum. Also, to increase robustness, the measurements include noise intentionally introduced by motion during data acquisition. Now Hannes will talk about our algorithms.
There are different machine learning algorithms for performing the classification task. We decided to use a simple approach, namely the k-nearest neighbors algorithm, because it can be easily implemented in low-performing devices, for instance, microcontrollers. Furthermore, to obtain better and more robust results, we have chosen neural networks as one of the most complex approaches. The k-nearest neighbor algorithm classifies data points using the n-nearest points with a predefined metric, for example the Euclidean distance. It is a simple algorithm and needs lower computational effort. We do not need much training except for preparing the main classes. K&N approaches have difficulties with high-dimensional data, especially if different data properties should be compared or if the Euclidean space is difficult to apply. Furthermore, the approach does not have many parameters to adjust the overall classification performance. In contrast, neural networks have thousands of parameters that have to be trained before being able to predict classes. Neural networks can be trained on domain-specific data. Thus, the network learns a distance metric by itself using the previous generated data. This leads, on the one hand, to more specified classification results, but on the other hand, it requires a high computational effort. Moreover, neural networks are able to reduce the influence of outliers because the optimal classification metric is learned. There are several neural network types available, for example the standard artificial neural network or convolutional neural networks. This variation leads to better adaptations regarding input data. The impedance spectra are available as input data. The data includes 1960 data points which can be classified by the Euclidean distance. All information is located in the same feature space and we do not need to weight them. Thus the K&N algorithm may lead to good classification results. We use K&N in two different approaches. First, the K&N1 classifies the data across the complete capacitance spectrum. Thus, all the data is used only once to predict the correct label. Secondly, we have found that the material information is weakly linked between the frequencies. Therefore, K&N2 classifies the test data frequency-wise, which may lead to a more robust prediction. The mean average precision curve shows that both approaches perform better the less neighbors are used. So k equals 1 for the best prediction. The classification of materials with the given input data is a comparatively simple task. K&N approaches are able accurately to predict the correct classes. Thus, using a neural network may lead to a high computational effort. We have kept the structure and parameterization very simple. Therefore, we use in the ANN and the one-dimensional CNN approaches the commonly used Adam optimizer to adjust the network weights. And we kept the learning rate constant over the whole training process. Our loss function is set to the categorical cross entropy, which also leads to the softmax function in the output layer. We use common activation functions like the sigmoid and Relo activation function. All these parameters can be adjusted in different ways and may influence the overall performance. However, this is out of scope of this project. We have focused on three different ANN structures. ANN1 and ANN2 consist of 3 layers with proportionally decreasing number of neurons according to the 1960 input features and the 10 output classes. ANN1 uses the sigmoid activation function, whereas ANN2 uses the Relo activation. We have also averaged and combined the input data to 300 frequencies, which reduces the input quantity and reduces the influence of outliers. The ANN3 network has less input features and therefore less neurons in the hidden layers compared to ANN1. Convolutional neural networks use kernels over the input data. 2D CNNs are mostly used to perform image classification tasks. Since we have got one-dimensional data, we can reduce the layers to one-dimensional CNNs. This reduces computational complexity and can be implemented on cheaper and simpler hardware. Our architecture consists of 3 hidden stages. The input vectors according to real and imaginary part are fed into a 100 neurons layer. Afterwards, a max pooling is used to filter less important features. We have also included one stage with 256 neurons and one with 100 neurons. Finally, a global average pooling and softmax layer is integrated. In our early work, we found that humans can classify some impedance spectra based on their plots. Thus, we use the plots as input images for state-of-the-art image classifiers like the Inception v3 and ResNet 18. In the following, I will describe how we prepare the image datasets. We have two 1D vectors representing the real and the imaginary part of the impedance spectrum. Of course, the data is not restricted to this information. The image classifiers need a specific image size to fit the resolution of the backbone convolutional neural network. However, we use the scale information and we have to encode this in the images itself. We use RGB images. Thus, we have 3 channels to encode information. The red channel represents the real values and the blue channel represents the imaginary values of the impedance spectra. We set the green channel to the maximum value. The brightness of each channel encodes the maximum value per dataset. With the preparation, we can generate our training and test datasets for the image classifiers. Images can encode a variety of information, and we have included 2 straight lines into the images. The red and blue lines, as shown in the right figure, represents the mean of each data vector normalized to the maximum and minimum of the dataset.
For the performance evaluation of the classification algorithms, 70% of the dataset are randomly selected as training data for each label, while the rest is equally split to evaluation and test data. The precision recall curve provides a general quality value of the algorithms. Note that the precision recall curve for KNN1 does not exist, since the algorithm only outputs a most similar class without precision values. Unlike KNN1, KNN2 classifies frequency-wise. A precision value can be calculated from the ratio of classification outputs from each frequency. The first curve shows the MAP for all algorithms where the MAP is above 0.95, while all underperforming algorithms are listed in the second plot. Here the algorithms with reduced input data show poor performance, as well as ANN3. The result indicates that important material information is lost due to the decrease in frequency resolution and also insufficient numbers of neurons in the networks. Since these networks have reduced neurons either in the output layer or hidden layers. This is especially supported by the significant underperformance in the precision recall curve of ANN3R, where the neural network has reduced neuron counts in both the input layer and hidden layers. The results of ANN1 and ANN2 are similar, thus showing that small changes in the network structure, for example, the sigmoid and the reload activation function, lead to small differences in the performance. Moreover, this shows the robustness of the network structure. In the well-performing group, the image recognition network shows exceptionally good performance compared to the standard neural networks KNN1 and ANN2. A look at the confusion matrices of these algorithms reveals that certain materials such as aluminum, steel, and water are difficult to differentiate because of their similar conductivity properties. Here, the image recognition-based methods outperform the 1D algorithms, especially Inception v3L and ResNet 18L. With their additional added horizontal lines in the images provide good results. KNN1 delivers unexpected good results for its simple algorithm and is comparable to ANN1 and ANN2. The robustness of Inception v3L and ResNet 18L should be highlighted, as a high percentage of measurements are noisy due to sliding motions during data acquisition. Overall, the results in this work are outperforming existing works based on tactile data, which indicate a higher material information content in the capacitive measurements compared to tactile measurements. In this paper, we evaluate different machine learning algorithms for material identification for sensor signals from capacitive proximity sensors. The conclusion of this paper is that simple machine learning algorithms provide good results for this task, especially when converting the 1D spectral data to images. Image-based CNNs are able to identify materials that are very similar in their electrical properties. In applications where fine granular identification is unnecessary, standard feed-forward neural networks or KNN algorithms provide reasonable results. Therefore, these algorithms can be implemented within the sensing hardware, since KNN only requires low computational effort and storage for the training data set. The detection is also very robust against noise generated by sliding motion during data acquisition. Therefore, the sensing method can be used for the presented applications, such as robotic feed, wrestling, and robotic vacuum cleaners, where motion is always present. A major drawback of machine learning algorithms compared to model-based approaches exists. when system conditions vary. A change in electrode design, for example, or circuit parameters requires a new training dataset, which is time-consuming to create. If you have any questions, feel free to contact us. Thank you for your attention. Bye.